Since childhood, mathematics has always been a passion of mine. I've spent hours exploring and playing with various functions like the sine, the logarithm, and many other functions through simple exercises. These functions have accompanied me throughout my academic journey and have allowed me to understand and appreciate the beauty of mathematics. However, my view of mathematics radically changed the day I discovered the story behind Gauss's famous formula for the sum of series terms. You know, that incredible formula that finds the sum of the first n natural numbers? Alright, a little reminder about this story is in order. Legend has it that the prodigious mathematician Carl Friedrich Gauss, while still a child, solved a problem given to him by his teacher to distract him. The teacher asked him to find the sum of numbers from 1 to 100, expecting it to occupy Gauss for quite some time. But Gauss, much to everyone's surprise, found the answer in just moments. He realized that the sum could be computed by strategically pairing numbers 1 plus 100, 2 plus 99, 3 plus 98, and so on, each pair resulting in 101. There are 50 such pairs, so multiplying 101 by 50 gives 50/50. This clever method can be generalized to find the sum of the first n natural numbers, and the resulting formula is s equals half of n times n plus 1. In this graph, let's place all points so that for each integer n, it corresponds to its image by the formula. This formula can be extended beyond integer numbers to be represented as a continuous function. Indeed, instead of just adding integers, we can consider a generalization that interpolates values between these integer points to form a quadratic curve f, where the function f of x equals half of x times x plus 1. And what about the product of the first n terms? It's called factorial of n, a positive integer n denoted by n factorial, the product of all positive integers from 1 up to n. For example, this expression allows determining the factorial of 5, which is 120. Here, we place all points corresponding to the factorial of each integer. Factorial plays a crucial role in many areas of mathematics, particularly in combinatorics, probability theory, and analysis. But can we find a formula expressing factorial using the same technique used to find the sum formula? It's much less obvious. Currently, there are no simple formula to express the factorial function. However, there is a link we can establish between factorial and this parameterized integral. By computationally approaching this integral across the complex domain, we can consider a generalization of n factorial beyond negative integers, which are poles of the function. Thus, we can trace the curve of factorial over the real numbers. By shifting the curve like this, we obtain a well-known function among mathematicians, gamma of x. Since the day I discovered this function, I have always wondered if it was possible to find a simple formula to express it and what the consequences of such a discovery would be. I then realized two things. Firstly, that it was pointless to search further than the positive part of gamma of x, because its negative part is deduced from its positive part. But most importantly, through this hypothetical expression, represented by the function x factorial over x, we could derive an expression from the gamma constant and zeta 3, without resorting to integrals or series. I then challenged myself to find this formula as Gauss did for additions. Let's embark on the quest for the factorial formula. Stirling's formula is an approximation used to estimate factorial values of large numbers. It's particularly useful in mathematics and statistics when dealing with very large numbers where exact factorial calculations become impractical. Stirling's formula is given by this expression. This formula shows us that the factorial of a number n can be approximated by an expression involving powers and square roots, significantly simplifying calculations. Using this approximation, we can obtain a very close estimate of the actual value of the factorial, even for very large values of n. Stirling thus offered an elegant and practical solution to bypass the complexity of exact factorial calculations. Although Stirling's formula is extremely useful for estimating factorials of large numbers, it has some drawbacks when attempting to generalize the factorial to all positive real numbers. We obtain a curve that does not match x factorial over x near 0 plus. Indeed, Stirling's formula does not provide a good approximation in this region, as it is primarily designed for large numbers. However, by examining the behavior of the factorial for values very close to 0, we can find an asymptote. In other words, even though Stirling's formula is inaccurate there exists an approximation that describes well the behavior of x factorial over x near 0. This approximation is given by the function 1 over x. Thus, although Stirling's formula is inaccurate at 0 plus, we can use 1 over x to obtain a correct estimation of the normalized factorial in this region. It's therefore necessary to use two distinct formulas to approximate x factorial over x. Stirling's formula for large values of x and the approximation 1 over x for values close to 0 plus. This allows us to have a good estimation of the normalized factorial both for small and large values of x, recognizing the limitations of each approximation in their respective domains. To address the need for using two distinct functions to approximate x factorial over x at 0 plus and plus infinity, I sought to find a single formula that is equivalent to x factorial over x in both these regions. After much research and testing, I managed to discover a formula that meets this requirement. It unifies the approaches into a single coherent and efficient expression. This formula is given by this equation represented by this curve. Thanks to this formula, we no longer need to use two separate approximations depending on the values of x. Moreover, it almost seems to coincide with the function x factorial over x. Impressive, isn't it? However, I foresee the skeptics coming. Indeed, it remains to be demonstrated that this function serves as an asymptote both at 0 plus and at plus infinity. Let's revisit the formula on the screen and break it down. It consists of three elements that we multiply together. 1 plus 1 over x raised to the power of negative x squared minus x over 2 plus 1 half, x raised to the power of x minus 1 half, and x times square root of 2 pi minus 1 times logarithm of 1 plus 1 over x plus 1. Placing Stirling's formula above, we notice they share the element x raised to the power of x minus 1 half. To demonstrate that our expression is asymptotically equivalent to x factorial over x as x tends to plus infinity, we will show these two assertions. Let's rewrite our problem to simplify it. To validate our equivalence, we need to determine the limit value of our expression to ensure it equals e. Now, let's move on to our second problem and verify that our expression tends to square root of 2 pi as x tends to plus infinity. We have successfully demonstrated that these two assertions are true. Our formula indeed equals x factorial over x as x tends to plus infinity. To demonstrate that the formula indeed equals x factorial over x as x approaches 0 plus, we need to prove this expression. As before, we will rewrite our problem. Let's calculate the limit of this term. Now, let's focus on this part of the formula and determine its limit as x approaches 0 plus. We perform a change of variable y equals 1 over x, which simplifies to determining this limit. By combining these terms, we indeed obtain the limit of our expression as 1, which implies its equivalence to x factorial over x as x approaches 0 plus. We now have a curve that approximates x factorial over x across both bounds. This unified new formula appears to offer increased precision compared to Stirling's formula, especially for large values of x. While I won't demonstrate this last assertion, the results are nonetheless promising. Let's now move on to the second part of the video, dedicated to two parameterized integrals that I have found and would like to share with you. The gamma function, an extension of the factorial function to real and complex numbers, is defined by a parameterized integral. It's typically represented as generalizing factorial values beyond positive integers and providing continuity in factorial computations. However, in the course of my research, I have discovered a simpler parameterized integral that preserves the essential properties of the gamma function. Here is the new integral I have uncovered. This integral, simpler than the one traditionally used to define the gamma function, opens up new and interesting perspectives. As an interesting side note, it's fascinating to observe that the famous Gaussian integral can be derived from this new integral. By substituting x with 1/2 and redefining the bounds to go from -infinity to +infinity to double the area under the curve, we obtain exactly the Gaussian integral. We know the result of this integral is square root of pi. Translating this result to our new integral would give us gamma of 3/2 equals square root of pi over 2. Enough with examples. Let's move on to the demonstration. Let's revisit our new integral and proceed with the change of variable by letting u equals t raised to the power of 1 over x. This implies that t equals u raised to the power of x. The change of variable has no effect on the bounds of the integral, and we can calculate the differentials of u and t. During my research, I have also come across an intriguing parameterized integral that I conjecture to be equivalent to be the absolute value function of x. This integral has captured my interest due to its apparent symmetry around the ordinate axis. However, despite several attempts, I have yet to prove this equivalence. I present it in the hope that someone may take up this challenge and determine if this conjecture holds mathematically. Who knows? Perhaps I'm missing a simple proof. I hope that my research will inspire other enthusiasts to delve deeper into these ideas and expand our understanding of special functions and parameterized integrals. Maybe we will uncover the secrets of these functions sooner than expected. As mentioned in the introduction, the negative part of the gamma function can be deduced from its positive part. To justify this claim, we will use the new formula proposed in the first part of this video. With this formula, we will be able to provide a consistent approximation of gamma of x across the entire real domain, while demonstrating that the negative part can be directly and logically derived from its positive part. To achieve this deduction, I will now introduce what I call the extension formula that I am displaying on the screen. This formula, which is merely an adjustment of Euler's reflection formula, will play a crucial role in our exploration to obtain an approximation of the gamma function over the entire real axis, excluding negative integers. By naming this formula as such, I aim to highlight its role in extending and generalizing the factorial function. But before that, let's demonstrate that this formula is true. The proof is very simple. We will proceed by verification, ensuring its validity over the interval from -infinity to 0, excluding negative integers, and over the interval from 0 to +infinity. On this interval, the sign of x is equals to -1, and absolute value of x is equals to -x. On this interval, the sign of x is equals to 1, and absolute value of x is equals to x. Now that we have demonstrated the validity of the formula, here is the process to obtain an equivalence of the gamma function. Now that we have demonstrated the truth of this extension formula and obtained an approximation of gamma over the entire real plane, you might wonder, what practical use does this formula serve in scientific progress? Well, let's be honest. This formula serves absolutely no practical purpose. It mainly serves to satisfy our mathematical curiosity and give us the pleasure of saying that we have a valid approximation of gamma everywhere. So practically speaking, this extension formula is mostly just for fun.